All right. Good morning, everyone, and welcome to today's class. A brief apology. I had an issue with my computer, the hardware, and that's what I was sorting out. We've been delayed a little bit, but don't worry because today's class is a little bit short. So we are still continuing with a single degree of freedom case, and I believe that this should be the last. This should be the last. A brief apology. I had sorry for the audio. Okay. This should be the last of the single degree of freedom, series, so that we can be able to go to multiple degree of freedom cases. We looked last week at when the forcing function is harmonic, but today we are going to look at a case when the forcing function is general. It's not harmonic, and we see how we address this.
We've been talking about the single degree of freedom dynamic system. So last time we were talking about forced vibration, and we talked about when the forcing function is harmonic. That is, it can be expressed as a sinusoidal wave. Now today we look at the second part, where now the forcing function is arbitrary, is general. Remember, we talked of cases when the forcing function is not harmonic, and we give a number of cases. You say, for example, could have the forcing function, the applied force being constant, or we had a case whereby we could have ramps, the force increases and then remains constant. The worst case scenario is when we just have a forcing function which cannot be described in any form. Because, for example, the case one here, this P, if you say this P naught, of course, now we know at any time F is equals to P naught. So Ft at any time is equals to P naught. Again, at this equation or this type of a forcing function, we found that you can be able to express it stepwise. From this part to at the time T is equals to, let's say, T naught, we can be able to express this one using the gradient and then the forcing is constant. So what we are saying is that these kind of forcing functions can be expressed analytically using analytical expression. But we have cases whereby the forcing function might not necessarily be expressed analytically. Maybe we find that a certain kind of a forcing function, maybe like an impact load, is behaving like that. So you find that this kind of function, we may not have an equation, an analytical expression, but it can be, for example, be expressed empirically from experiment, like P or F is equals to P 0.1, P plus blah, 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 like that. And empirical equations are those that are obtained that cannot be derived from first principles, and they are obtained from experiments. So if you go from an experiment, you determine like a certain function varies, or there are some parameters. Let's say like a force F depends with time and also mass, and also maybe something else like acceleration, but you don't know what are these coefficients. So you have the coefficient A, another coefficient B, like that. Then through a number of experiments, you are going to determine these coefficients. So that now you have this function, which we say it has been derived empirically from experimental observations. Okay, so this kind of forcing function we want to see if the dynamic motion is being initiated and progresses as a result of a forcing function, which is arbitrary, then how do we go about analyzing that motion? Let's consider a general case here. We have variation of force P with the time. So this kind of analysis where we are analyzing, for example, force or any displacement with time, we talk of like we are in the time domain. We could analyze in something called frequency domain. Let's just stick to analysis in the time domain, where force is varying with the time as shown. So this curve, the curve we are seeing here, is the one that this is the arbitrary form of our forcing function. Now, time t. So this is the axis or the x-axis is time, and the coordinate is the applied force. So at time t is equal to tau. So at this point, the force, you can calculate this force as p tau. So now we want to see this force now applied at this time. Assume our system, from all this time, from time 0 up to tau, there was no exam or gravitation, but at this point, we apply a force at a very short time, d tau or delta tau. What this means, for example, let's say we have somebody playing golf, and then there is the golf ball here. So he just swings. At the time he is swinging his bat or his, and then before he comes to hit this golf ball or cricket, there is a time lapse from time zero, the time of swing. If you started analyzing our motion, from the time he started swinging his bat until he hit, there will be some time allowed, and the force will only be at this time T no. Now this is instantaneous time because it will, the impact, what you call the impulse, will be applied, or the force will be applied to this ball on a very short time. So we call that's why we are putting this shaded part here a short time, the tau. And now the forcing function will only be experienced for the motion past tau. After this part, this is now when the forcing function starts acting. Before, in this region, there was no force. This was a time when he was just swinging his back. So the motion or the response is as follows. After this point, T is equal to tau. So you can see the motion now will vary like this. This is what we are calling the response. At the DU here, you should take note to note that DU represents the time history response. This shows the time history response. This is not a derivative. This is not derivation. We are just showing it as a time history of a small time or an impulse. Okay. Remember, impulse is equal to time force applied times time. This is why I'm giving this is the impulse, and therefore the resulting response, that is the resulting displacement. Remember, response could be displacement, could be force. But in our case, we are sticking with displacement. This D, which I insist this D is not derivative, but the response due to the momentarily applied force is equal to this expression here. So you see now the motion is sinusoidal here because of the applied force, and expressed using this. When T, and this one is only for the case past T greater than tau. This is for this, and that's why you find that the time that we are considering the x-axis or the horizontal axis for our response considers the time t minus tau. It considers this time. You know, the overall time is t, but we are negating time tau. Tau is the time before that the force was applied. Okay, so, and this is now our response. So now we have the response because of the momentarily or for that impulse, the response due to this impact. Okay, equation 79. Now for us to analyze for the total motion for the overall, now, past that, because it will continue influencing other part, the external applied force, we can have summation of these small instances of time. If we keep the time interval the same, beta, such that the total response for the entire loading history, is, now the entire loading history is for the overall time. But we know, of course, that the time when the force is experienced is when T is greater than tau. And that's why in our expression, we have this time T, the period, there is what we can kind of, what we are seeing here, there's negation of this part. So that even in our integral, although we are integrating from the time T is equals to 0, overall up to the time T is equals to the end of the loading period that we are considering here, we know, of course, because of this part here, that the force or our motion will only be experiencing the externally applied force or the forcing function when T exceeds tau. Now, this is now at the total response or the solution to our motion, which is called the Duhamel's integral. If the initial condition are such that or the initial displacement is not equals to 0, okay? If the initial displacement is not equals to 0, the initial velocity is not equal to 0, we shall have an additional free vibration. What does that mean? That means, remember, free vibration was initiated by initial conditions. So at the initial condition, brought about by the initial displacement. Remember the swinging pendulum. This is our pendulum, and at this point, replace our ball here. This is a ball, and then this is a swinging pendulum. Let's say it's fixed here. So we want to initiate this motion, or we want to set this ball into motion, and by so doing, we have an initial displacement, which is not equals to 0. That is, we make that small initial displacement, and then this pendulum or this will come swinging, so that now it can come and hit our ball here. So because of this initial displacement, there is the free vibration that you and then once it hits this ball, or let me just say this is not a ball, let me fix it at the bottom here. Let me fix this. Let me give you an example of demolishing a house. We have a house here. You have seen houses being destroyed. Usually in Kenya, which is very risky, you find like an excavator is the one that goes to demolish houses. If, for example, they have some illegal structures. So you find like the excavator is at this point, and the operator is trying to hit this building here. So this structure can collapse on him. You find like, for example, example, if you observe the Chinese, when they are constructing, they're demolishing some structures. They have some machine positioned at a distance, and they have got a very high crane, and then we have like some suspended weight which can swing to hit this building. So this allows the structure or the machine to be positioned at a distance, and then this can swing to and fro, and it hits this building up to collapse. So what we are saying is that at the initiation, when the first impact to this building will be this, the swinging part, the weight have to be displaced at a distance. Then it comes and hit this wall. So there is the free motion that initiates, then comes, then because of this weight, it hits the structure. This structure is set into dynamic motion. So the response of this structure will be a combination of the free vibration because of the initial condition, initial displacement, plus the forced vibration due to the impact of this weight on the structure. This is the part we are saying here. So now this is why we are saying if the initial conditions are that we have displacement and the velocity not equals to 0, then we have to add the free vibration response. This is from equation 16 in your notes, and this is the green part. This is the solution to free vibration of motion, and now this is a solution due to forced vibration with arbitrary loading. This is the Duhamel's integral here part. Now, this is the part I wanted to mention about the arbitrary loading. In case the tau or the arbitrary load is empirical, that is not analytical. So if it was analytical, for example, if the loading function, analytical meaning we have an analytical expression. If this loading function was like constant, a straight line, because now you'll be knowing that P is equals to, let's say like P note, if this is P note here, okay? Or if it was something like that, we can be able to express. If you look at your note, I gave an example of an analytical equation. So if it's not analytical, then it means that this integral can only be evaluated numerically. So we'll be coming to cases whereby we may need to use approximation method of solution of numerical equations like sinusoidal rules, trapezoidal rules, or simple summation, etc., etc. So that's why we are saying if this is not empirical, then Duhamel integral have to be evaluated analytically. Now let's simplify this expression so that we can be able now to analyze that, because that is now what we are just doing in our section here, or in our analysis here about arbitrary loading. Arbitrary loading, we assume them that they are empirical for our case. So you trace this trigonometric identity. This one, of course, we use it to expand and also to factor or to simplify our expression. So if this is the case, and then you assume the case when U note and V note is 0, so that we can ignore this part of free vibration. We had already analyzed this part before, so we can ignore. We just want to be left with the Duhamel's integral with no free vibration. Therefore, this equation 8 can be expanded. This part here can be expanded using this trigonometric identity, so that we have sine and cos. So we have this part, and again, expanding it in this form, we can now simplify it further to this form here. You see, it's a very simple form now. Here becomes equation 82, where A, the whole of this part, we can call it A, and in the notes that I have given you is A bar, and this part here, the integral, is B, such that now our equation simplified, the Duhamel's integral becomes very simple, and it looks similar to the equation that you have been handling, where A is this part and B is that. So our work here now is to evaluate what is A, what is B, so that we can be able to solve the response of our forced vibration with arbitrary loading function. So of course, numerical integration, we are assuming that this is empirical. It cannot be expressed using analytical function. So you see, we are saying the loading P tau may be varying like that. So we need to subdivide it into equal segments with different ordinates. And we said this is a variation of the cos. So we are saying again, A is as given here. We can simplify it as we set this part P tau cos omega tau to be equals to Y tau, the function Y tau. So that now this cos omega tau is this curve. This is just for illustration. And then this is the P, and the last graph is the combination P T cos or P tau cos omega tau. This should be tau. You can correct this part here. So now you're just doing the normal thing that you have been doing before, say numerical analysis, approximation method. You can use either trapezoidal or Simpson's rules or simple summation. So these are both dividing into simple into equal intervals, and then same or the ordinate, the number of ordinates will depend. The number of ordinates, these vertical these divisions, we call them ordinates. This axis is called the ordinate. The horizontal is called the abscissa, because we do not always say the x and y, because we may not be using those terms. All right. If we divide, we have divided into equal increment of time, delta tau. So the integral this integral, this is a continuous integral, yeah, continuous function. You see this integration function. So this continuous integral function in discrete form is the same as the summation. Remember, integration is just summation from 0 to t. This is what this table means. It's addition. So for a continuous function, now we have subdivided it into discrete functions. You remember when we subdivide, it's like we are adding. So this becomes a small horizontal line. So if you have the time interval being too great, if, for example, the time interval was between that region, so you have a straight line connecting these 2 points only. So if this was our selected time interval, delta tau, you see the curved part is the actual solution, but we are just approximating using a straight line. So it means the deviation of the actual solution to the approximation becomes significant. That's why we need to have as many subdivision as possible, or we use the time interval so that our answer, our approximation is as close as possible to the actual solution. Okay, so the choice when you are solving this, remember, in actual analysis and actual structure and in the field, you shall be using software, so you not be limited. You can have as less time as possible so that you can have your solution. And this is the same case with with finite element analysis that we are using last semester. And the same numerical analysis softwares, we can apply it in this course, dynamic analysis. So we talk of refining the mesh size, refining or reducing the element size so that we can have our answer converging or coming as close as possible to the actual solution. Remember, why we don't have the actual, we cannot be able to do the actual solution is because the solution or the expression of this function cannot be analyzed analytically. Okay, we cannot integrate it. Like if we had this variation of the forcing function is like p is equals to sine t, or even like p is equals to p naught, then this equation could be p naught sine omega t. And this one we can integrate exact. We can have a closed form solution or an exact solution. But in this case, we are saying the value p or the function p could be 2t plus 0.73 p naught over 1 plus, such that you find like this is just from the experiment, and analytical integration of this function may not be feasible. Okay, I hope you are still together up to that point. So you have seen we just need to summate, to do the summation, and then we approximate by summing the ordinate. So the value a, this AT, where T is the summation of n is the number of subdivision times the time interval nt. So that's why we are using these symbols. This is equivalent. So we are saying an, this is the discrete form, an can be able to approximate the continuous AT. Of course, this is the integral we are analyzing. If we subdivide this into different intervals, intervals of time, and then we apply this method, sinusoidal or trapezoidal, etc., etc. If, for example, we are using the Simpson's rules, this is just a restatement of the Simpson rule, which have been modified to fit our case here. We have, again, I'm using this table, which talks of is almost equals to, because remember this part here, we have delta tau, 3m omega, these are constant, and then we have these are the ordinates. Remember the weighting function, we have m1 and m2 as the weighting function. This is 1, 4, 2, 4, 2, 4, and the last one becomes 1. So n is equal to 4, 6, it's even. Where n, these are the number of division, which is equal to total time divided by the time interval that you have chosen, must be an even number for Simpson's rule to be applied. So of course, we can condense this equation because it's repetitive. So we are saying if we express it in its recursive form, equation 83 can be expressed in condensed form as shown here. This is equation 84. This is the same as this one, but this part we have condensed it to be, because we are saying it's recursive or repetitive. So we have been able to approximate AT, the continuous form of the integral, by doing the summation. So this is an approximation using the approximation method, the Simpson's rule. You can use the trapezoidal, you can try. And you know, of course, the advantages and disadvantages of different methods in terms of the accuracy. Again, BT, remember we are analyzing this equation 82. So you need to find this, and then this one. That's what you can evaluate everything to solve what is the response as the time interval. When we talk about the response, I hope by now you know what we are talking about. The response. The response is how is that structure going to respond, and what can we measure in response. One of them is the displacement. That once we apply that load on a structure, like in our building or a photo frame, what will be, we may want to know what is the maximum displacement, or what is the displacement at this time, or what is the force experienced in that structure at this time. That is what we call the response. So you might find like we are talking of the response in terms of force or the structure, but we are also using a forcing function. That is, there is a forcing function applying a force on a structure. So you want to see what is the force, internal force experience of that structure. In our case here, I found it necessary for ease of understanding to focus on response in terms of the displacement. What is the displacement, maximum displacement, or the minimum displacement, or what is the displacement? Of course, we are not interested in minimum. Maximum is the worst case scenario. So that we know in our design, is the maximum displacement induced by that externally applied force sustainable by our structure, because we know the material characteristic. If it's a concrete structure, a concrete column, will they be able to take in that displacement? Is it allowable in our design, or the structure will fail? If not, what can we do? So if we are analyzing, because this dynamic analysis mostly will be dynamic loads, for example, seismic analysis, wind loading, impact loading. That's why now we start thinking of alternative materials or structural systems, whereby you may think of using concrete filled steel tubes for our column, because we know steel is a bit ductile, more ductile compared to concrete, and it cannot be able to take more deformation than a rigid concrete structure. So that's why we are doing this type of analysis. We may also want to know at this time t is equal to maybe 5 seconds, what will be the displacement? Will the displacement be within our allowable limits? That is the response we are analyzing. We say now BT, again, you can express it in terms of in a discrete form, Bn, just the same way you express An. And in this case now, y tau, or the function y tau, the integral part will be equals to sine. Of course, this part, A is t, of course, sorry, here you need correction. Here you may need some correction. In your notes, the one I gave you on page 88, we have the first part. So if this, of course, this is our A. This is cos, then this should be cos. Let's go back. Let's just go back slightly. We see that A. Oh yeah, it's correct. It's correct. The notes are okay. So because A is this part, so I was looking at this sinusoidal part. So of course the B now is the one that we are calling y tau. This is the integral that we are evaluating. So in our analysis now, we are saying B can also be evaluated in a similar manner. So we need to express B in BT, the continuous BT, in discrete form Bn, and then we set Y will that. Finally, the total response of the overall system will be U. So we are saying UT, the continuous UT response, the equation 82, this one, UT, can be approximated as UN here. You remember UN is this N represent the number of division or the component, and is as given by. So this is the discrete form of equation 82. Equation 82 is continuous, 85 is the discrete form. We have evaluated this integral AN, BN, and now the T time T. T was continuous throughout. Now we want time at discrete point. So at time T1, T2, we apply like that. So that now this the total response. We can be able to know what will be the displacement at a certain time, what will be the maximum displacement, and what is the displacement for the overall. And after we do that analysis, we have the displacement at different points. We can know for our structure, at different point in time, we can plot the variation of the displacement in terms of a curve. Our response can now be expressed in terms of displacement, U, and time T at different time intervals. So initially, analytically, we could have a smooth curve, but now we are talking of the response will be in discrete form. So you might not see it. If your time interval is small enough, the discrete form may be, the sharp curve may not be seen. If the interval is small enough, then it will be almost as it's continuous. Now, something to mention is that the approach that you are using can only be applied to linear systems. A linear system is considered as steel, our steel column. If we have a rigid approach frame like that, or a frame, and then carrying a platform there, then we have an impact loading there. It could be a bomb blast, we act on a short time. So our structure will deform, and then it shall have a to and fro motion. This is on the other. So with having to and fro motion, which will continue dying due to damping. What we are saying is we are restricting our motion. This displacement is for the elastic ridge. This response, because the impacts act on a very short time, and we are adding those small impacts of time. So we are saying we are adding individual responses. Our structure, we are not considering the region when there could be permanent deformation of our steel structure. So we are assuming that our steel column they are acting within the elastic ridge. That is, they can be able to come back to the original position. There will be no permanent damage. I hope that one becomes a bit clearer as we go forward. Because later on in future studies, you'll be talking of nonlinear analysis. And most of the studies that Actually, I think in almost all of the theory of structures, the work that you have done, you have been dwelling on the elastic linear or elastic ridge, linear system. Because by the time most design that you are doing, strength design, ultimately limit state. So we design maybe serviceability limit state. We want the structure, even if there is vibration or deflection, to remain or to go back to its original position. We don't want our steel beams to sag and to remain sagging. But we know for studies like earthquake design, we may allow for that. For dynamic, what we do not want to occur is the collapse, total collapse. But we want to see the ductility, how much maximum load can be sustained before a structure collapses, because we are talking of safety to people, the occupants. So in that case, the analysis we are just talking of small impasse due to time interval, summation of different small time intervals. So the application of this equation is only limited for linear systems. So let's see how we can apply now this equation, or these steps that you have explained. How can we analyze the response due to the arbitrary applied dynamic load in an actual example? All right. So this example, we want us to go through it very quickly. Another thing I wanted to mention is that I know right now you are seeing KIPS. This is an empirical unit. When you see kilopounds and you see feet, of course, this is mostly from an American book. Those people who follow, or those nations which follow empirical system and the American system, of course, for us Kenyans, we are in the British system. So we are in metric. Usually we use the metric unit. But that does not mean anything. We can go ahead and do the solution. Let's look at this example. I know as we continue, you'll be able to comprehend much. We want to solve this. There is just a small handout, just one page handout that I have given to your class rep this morning. So you can share with that. It's the same thing that I'm going to project here, but it's a table. And when you project on screen, if you're using a phone, you might find like it's very minute. That's why I had shared that, because it's this table. I've shared this table. So for those people on desktop, then it's okay. But if you're on phone, you need maybe to print out that so that you can follow through. So you want to solve to obtain what is the response. And you are clearly told the response that you have to calculate is force history. Force history. What does that mean? That means that we want to get the behavior. So this is a force. Now this is not displacement. We are told now after you see there is an impact, an impact or a load that have been maybe a blast loading momentarily. You see this is 0.05 of a second. It's a very small time. It acted on this water tank momentarily because it's a blast. So what you are required now to obtain in terms of the response is the force history. With the time, what is the internal force that is experienced on this structure? How will the force vary? Okay, so you're not on the display. So it's be about the force on this side, and then of course the time, because we are talking of history. Okay, and then our solution, of course, this was part of the solution. We are saying you assume, because our total time that the load is acting it's acting like this. You are given the time history. I mean this forcing function, how it's varying, and for a total time of 0.5 seconds, the maximum occurs at 0.025. Now, for us to use the Simpson's rule to evaluate this, of course, Simpson's rule, you know that we need to subdivide this into a number of using a number of ordinates, and for us now we have taken a time interval 0.005, small time interval, that is delta tau. Okay, we are going to forget about the second part, but you can look at it later on. Okay, and then this is just a normal procedure that we use, or we follow when we are working out the Simpsons, when you're using the Simpsons rule. And for that case, you can see we are looking at like how we evaluated AN. We are going to obtain what is AN, what is AN, what is BN. Using BN, remember BN is an approximation of the BT, of the continuous function BT. And remember BN and BT, these are condensed format, of course. These are the Duhamels. I have found another book saying, another pronunciation saying Duhamels integral.
So however you choose to pronounce that is not a big issue. So this is a part that we are focused on, because the p tau, this is what he's saying, this is not numerical, it's not analytical. Okay. So what you need to do, you see this breakdown, you already know what is A and what is B, what is AN, what is B. So we need to evaluate all this. These are concept data for 3M omega. We need to go to what is the ordinate Y naught for Y1 and all that, and then we do the summation. And then we can use the equation 85 to get what is the response in terms of the displacement. If it's false, of course, remember the F is equals to K, because we are within the linear range. We have talked of this analysis, or this Duhamel's integral being applicable in the linear range. So of course we know that Hooke's law apply in that range. So for the force, once you get the displacement, we know that force is equals to K times displacement. So you just need to divide to multiply U with K, the stiffness, to be able to get the force, right? So it's as easy as it can be. And allow me now to just show you this. So you need a number of things, because what you need to see or to understand. Let me project this. Let me project this using my bigger slide that I have shared. Yeah, this is what I have shared with you. And we are saying the first thing that we have, if you look at this, n is the number of the ordinates, and they have to be even. For Simpson's rule to apply, for trapezoidal rule, odd, and so on. So all that we are doing here, which I don't think it's so necessary to go through it completely.